Hello everyone, and welcome back. In this video, we're going to be tackling the topic of CISC versus RISC. So, what's CISC, what's RISC, and why should you care? Well, if you remember in the last video, we talked all about instruction sets. What it is, what it's used for, why it's important, blah blah blah, yada yada yada. And if you don't remember all that stuff, you can go back and watch it again. But what CISC and RISC are, is they're sort of like the two flavors of instruction sets, if you will. You can either have a CISC-style instruction set, or you can have a RISC-style instruction set. And these aren't absolutes. Nothing in life is an absolute. I mean, if you really wanted to, you could go in and you can invent your own wacky instruction set that wouldn't really fall into either of these categories, and then you can laugh in the face of the people who invented the RISC and CISC categories and run off or something. I don't know. But the whole point is, pretty much every instruction set falls into one of these two categories. Not absolutely every instruction set, but most of them do. So, what are they? What do they mean? And when would you use one over the other? So let's start talking about CISC. What is CISC? Why is it important? What does it mean? Well, CISC, believe it or not, it's an acronym. Like just about every single thing in computing, because they love acronyms for some reason. So, CISC stands for complex, except actually spelled correctly, complex instruction set computing. And I know you're definitely not going to get this from the name, but CISC instruction sets are categorized by having really complex instructions built in. Now, don't be confused here. It doesn't mean complex as in you need this really advanced binary code, or you have this binary code which can execute like 10 million things at once. No. It means complex in the sense that the overall operation that the instruction is doing is complex. Like, for example, you might have an instruction that takes register A and converts it into its BCD equivalent. That would be a complex instruction. Or maybe it converts it to a floating point number. And lots of conversions are complex, so you can do floating point conversions, you can do conversions between ASCII and Unicode or something. I believe I actually used that example before, but yeah. And also some operations are really complex, like maybe you want to do the inf root of something. Maybe you want to do a floating point root of an integer number for some reason. I don't know. But basically the idea is you want to have lots of really high-level complex instructions in the instruction set. Because the ultimate goal is for someone to sit down and actually program for this computer. So you want to make their job as easy as possible. And the way you're going to do that is by making as advanced instructions as you possibly can in the instruction set. So that way, they're writing the code and they're like, oh no, I need to convert BCD. There's an instruction for that. You want to write floating point calculation where you take the floating point root of an integer number. You just, oh no, there's an instruction for that. You want to convert between audio formats? There's an instruction for that. And it's usually not quite as extreme as I'm making it out to be. Usually you won't go quite as far as just having like conversions for absolutely everything and such, but ideally you'll have some really complex instruction for things that'll be common. I think BCD is probably the most realistic of all the examples I've given here. But yeah, that's the idea of CISC instructions. So what's the advantages of doing instructions like this? Well, as the design philosophy goes, it does make really, really easy to program computers. Like, you can sit down and make a really high-level advanced program in just a couple lines of code for a CISC computer. So this is a really good instruction set for a programmer because they can just sit down, they can write programs in like 2 lines of code. They've recreated Snake or something. Yeah, again, that's a little bit of an exaggeration, but you get the idea. You can do a lot of stuff with very, very little code. And as a result of that, it's also relatively memory efficient because you don't need to store as much code in order to execute your actual program. So CISC, very, very, very useful for programming. If you have any difficulty at all programming, you'll feel right at home in a CISC instruction set. They're incredibly easy to program because pretty much any instruction you want is right there. It's it's almost like programming in Python because I know someone's going to make that reference, but I'm doing it for you. It's set up so it's really easy for you. So yeah, now that's the real advantage of CISC, but it does have a bit of a cost to that. When you are writing a CISC instruction set, you have to go in knowing that no matter how you do it, it's going to take a performance hit just by nature. Because doing BCD conversions doesn't matter how you cut it. That's going to be a really expensive operation. You want to take floating point roots? Yeah, good luck with that. You're not going to make that happen in 3 ticks. It's going to take several hundred ticks for that operation to complete. So you will have a performance hit when writing CISC instructions. Now that doesn't mean every instruction will be 200 ticks. If you're still doing an addition operation, that's still going to be fast. So, I mean, simple instructions will still be fast, but you have to go into these things knowing that it's really easy to make a CISC program that will run inevitably really slow because you do have access to all these really complex instructions that do everything for you. And you may be using the really expensive instructions rather than the simpler instructions simply because of that. So there is a bit of a performance hit. Now, it's not terribly bad performance hit, but I think it's realistic to expect a CISC computer to run along the speeds of the Red Game series. They aren't really laid out like CISC computers, but they sort of perform like them. So that's sort of a good baseline for the type of speed you'll expect from a CISC computer. They do run relatively slowly. And again, usually that won't be for every instruction. Usually simpler instructions will run faster on CISC processors. But, yeah, you can have some really, really expensive instructions in CISC. And that's the first penalty. The other sort of penalty that comes along with it is just size and complexity. Because also the hardware for this stuff, you're going to have to build all the hardware for this stuff, or at least runs a subroutine that does it for you. And if you do that, inevitably, yeah, it's going to get crazy. You'll have this absolutely massive processor. Now, it's going to be really powerful, it's going to be really easy to program, but it's going to be pretty big. And it's also going to be a little bit more complex than usual, because you'll have to deal with, okay, if it's doing BCD, that'll have this pretty much completely unique case, and you'll have lots of exceptions and stuff, but yeah. So it does have some penalties, but again, the advantage is it makes it incredibly easy to program, and the programs are really memory efficient, and it's really easy to get something really high level working in CISC. So that's really what CISC instructions are like, and what they're used for. If you want some examples of real life CISC processors, any Intel or AMD processor pretty much is CISC. And the big reason they choose that is pretty much because the earliest ones they did were CISC, so they're doing it because they're sticking with it. But even still, those are some really CISC processors. And if you ever worked with x86 assembly language, you'll know what I'm talking about. There's some pretty ridiculous instructions in there. Just throwing that out there. But yeah, and that's really the big example of real-life CISC processors. But yeah, so that's pretty much all there is to CISC. Hopefully you understand. So if you're thinking about CISC, if you don't really care that much if your computer's runs at 3 ticks or something, if you don't care that it's going to be a little bit bigger than usual, and you just care that I want something that's easy to program, and I want something that doesn't take up 10 million bytes of memory to do what I want, and I want to do high-level things pretty simply, CISC, probably the instruction set for you. So, what about the other end of the spectrum? What's RISC? When would I want to use RISC over CISC? Is RISC better than CISC in insert case X here? Well, let's find out. So, first off, like CISC, RISC, it's an acronym, because computer scientists love their acronyms. What does it mean? Well, it means Reduced Instruction Set Computing. So, notice similarity in the naming? Yep. The big difference between CISC and RISC is RISC doesn't believe in having these absolutely giant complex instructions. You want to do BCD conversions on RISC. You want to take the inf floating point root of a integer number. So what? You have a computer in front of you. Program your computer to do it. You don't need to integrate that into the processor. It's not... When will you ever do that in most situations? You're not going to do it all the time, so in the times when it does come up, just program the computer to do it. Why not? That's sort of the idea behind the RISC system. Except probably a little bit less whiny than that. So, yeah, that's sort of the idea behind RISC. You don't want to have these big complex instructions because it does add all that bulk to your processor. It makes things bigger, makes things more complicated, makes things harder. You don't want to sit around and wait. You don't want to deal with that. You don't want to deal with having to implement these big, complex things into the hardware when you can just program the computer to do it. Especially since you're not going to be spending all your time doing BCD conversions or doing inf floating point roots or such. So, yeah, that's the philosophy behind RISC. As a result of that, RISC processors end up being really fast. And here's why. If you don't have to handle doing these 200 tick instructions every now and then, if they just simply don't exist, then most of the stuff you're doing is pretty simple instructions. You're doing what? Addition, subtraction, and, or, XOR, XNOR, stuff like that. All those instructions are 3-tick operations. All the instructions you're doing are incredibly simple. So RISC instructions execute lightning fast. You can make a RISC processor run at just absolutely ludicrous speed. They run crazy fast. And that's because, again, instructions super simple. And also makes things like pipelining, which is a hardware acceleration technique, if you're willing to call it that. Pipelining and stuff, tons easier on RISC machines. And since you aren't handling as many complex cases, it also speeds things up. So there's lots of really subtle things that go with the reduced instruction set philosophy that make RISC instructions just run crazy fast. So there's that, and also takes off all the extra bulk of having the extra hardware and extra complexity out of it. So they're a lot simpler to build and implement. So that's really the big selling point of RISC machines. Here's sort of the catch, though. You don't have really high-level instructions that you can just say, okay, I want BC conversions, do it for me. No. If you want to program a RISC machine, you're going to have a little bit more of a challenge than if you're programming a CISC machine. You're going to have to manually program to do BCE conversions. If you want that floating point thing, you're going to have to manually program it in. Also, since you are dealing with mostly simpler instructions like addition and subtraction and logical functions, since those are your primary instructions in RISC machines, you need more instructions to get simple things done. Well, not simple things. Simple things are already done for you. But you need more instructions to get things that would automatically be handled in CISC machines for you. So if you did BCD conversions, that might be one instruction in a CISC machine. It might be 7 or 8 instructions in a RISC machine. So you need more instructions to execute. Yeah. And that's really sort of the downside to RISC machines. You will need more instructions. They are a bit harder to program since you do need to manually think out, this is how BCD conversion works, this is how I program it in. I'm really overusing that example, aren't I? Yeah. But you get the idea, and that's all that matters. So, yeah, you will have harder times programming RISC machines. That's the really big downfall to them. But again, you get extra speed, you get simpler processor, and you can pipeline easier, you can implement acceleration easier, because the whole thing's just simpler overall. And I would like to just emphasize the fact that CISC doesn't mean it does more than RISC. It just means it has more integrated into the hardware than RISC. You can still do everything you can on a CISC machine on a RISC machine. It's just, if you want to do it on RISC, you have to sit down and program it yourself. So yeah, now those are really the two instruction sets. If you want an example of a RISC hardware in real life, if you have a smartphone, if you have an Android phone, for example, those all use ARM processors, and ARM processors, that's right, they're RISC machines. So most phones and tablets nowadays, they use RISC machines. And also, a lot of supercomputers use RISC machines. And I also know that the Sony PlayStation and PlayStation 2, they both use RISC processors in them. So those are some real life examples of RISC machines. Those are all RISCs. So yeah. So you have CISC, which is easier to program, and you have RISC, which runs lightning fast. CISC uses more memory. RISC... Wait, so CISC uses a lot less memory. RISC uses a little bit more memory. So, take your pick. So I didn't actually just consider anything for RISC. So, if you're thinking about RISC, here's the thing you should consider. If you just want something that's nice, simple to build, and it still gets everything done, if you want something that's really fast, and you don't really care that much if you need extra memory or a few extra instructions to get things done, RISC is probably the instruction set for you. Now, which one's better? Is CISC better than RISC? Well, take your pick, really. It's a matter of choice. Is chocolate ice cream better than vanilla ice cream? Who knows? Did the chicken come before the egg? It's one of those type of issues. Which one you choose really depends on what you're using it for, and yeah. So, yeah, it just depends. That's the ultimate answer. It depends. Sometimes you'll want absolutely lightning fast things, maybe building a supercomputer. RISC, probably your weapon of choice. If you're just building something where you need to write this super high level application, CISC might be better for that. It all depends on what the application is. And I guess this is all spiraling down to this one ultimate question. Which one am I going to use? Because I could go either way at this point. I could do this CISC processor, and I could make this really complex thing that does a whole bunch of super cool operations in the hardware, and that'd be pretty cool. It would run a little bit slower than normal, but it'd be easy to program, be high level, be really cool. Same advantages of CISC. I could do a RISC machine. That would be lightning fast, and it could do... Yeah, I'm not going to list over the advantages again, because I've already done that. I think you understand the advantages of CISC and RISC at this point. But, I will say, this tutorial is called the Advanced Redstone Computer Series, not the Advanced Instruction Set Series. I'm not going to be sitting down and designing this super advanced instruction set in front of you, because that's a whole new ballgame. I don't want to sit down and tell you how instruction sets are designed and such, because that could get into its entire... That deserves a series of its own. If you're interested in learning how instruction sets are designed and what makes a good instruction set, hey, post it in a comment, get support for it, and maybe I'll do a series on it, and you can start figuring out how you can design your own instruction sets, figuring out which instructions are most optimal to include, and which ones should be excluded, and how you should implement them, all the joys of designing your instruction set. But that sort of leads to the ultimate point. I have already designed an instruction set for this series, and I've gone with a RISC machine. The big reason is simplicity. I don't want to build a series where I'm talking about how BCD works, I'm talking about how floating point works. If I'm doing a series with a CISC machine, it's going to bring up a whole bunch of topics which really deserve their own series. So I'm sticking with RISC for the series. I've designed my own RISC instruction set. It's called Standard Redstone Computer Instruction Set. I talked about it in one of my updates videos. And I'm actually using CISC 2. That's the acronym, Standard Redstone Computer Instruction Set, SRCIS, CISC. And yeah, I've designed version 2 because the first one I realized way too complicated. It did more than it needed to. CISC 2, whole bunch simpler. I think you're going to like it. So in the next video, I'm going to start talking about the instruction set we're going to use, because that's an important thing to know. Now, is CISC the right instruction set for your computer? Will you absolutely need to use CISC and it be the absolute be-all, end-all of instructions? No. There's always advantages of using different types of instruction sets, and it's really hard to make an instruction set that encapsulates every possible case. I think I did a pretty good job of making an instruction set that does pretty much everything you need and can easily be used to do just about anything you want with relative ease. But again, that's sort of getting into the next video, and I'll get to that when I get to it. So, thank you, hope you enjoyed, and I'll see you in the next video where we'll start talking about the circus and how it works. And yeah, so thank you, see you then.